Hi everyone, thanks for joining us today. I'll try to make this session as interesting and practical as possible. Uh, we are like talking about something that sounds simple but can get messy and real quick. Not handling node churn in Karpenter. So I'm Chetan Saini, a software engineer at Antra, currently working with Expedia Group for over a year now. I was supposed to be joined here by my talented colleague Shivani Mehrotra. Due to a medical situation, she's not able to make it. But she's still a very much part of this talk. You will see her contribution through a pre-recorded segment included in the upcoming slides. Before we dive in, here's a quick look at what we are going to cover today. Understanding Karpenter, like what is Karpenter, node churning, like why actually node churning is a challenge. Then our approach, like what configuration we use, like how we tune Karpenter configuration for us. Then result and analysis, and then follow with the Q&A if time permits. Understanding Karpenter. What is Karpenter? Karpenter is an open source, flexible, and high performance autoscaler designed especially for the Kubernetes clusters. Karpenter is developed by the AWS. But it is not limited for the AWS environments. It can work with any of the Kubernetes cluster. It improves application availability by ensuring pods get scheduled quickly, and it enhances cluster efficiency. How does Karpenter work? So Karpenter continuously watches the pod that the Kubernetes scheduler marks as unschedulable, meaning they cannot be scheduled or placed on any of the existing node. And it evaluates the pod's resource requirements such as CPU, memory, storage to understand like what kind of node it is actually needed. Then based on that evaluation, Karpenter determines the most efficient node type and configuration for the pod. Unlike the other autoscaler that depends on predefined node groups, ASG, Karpenter provisions, and nodes directly, right? So, which gives it more flexibility and speed. Karpenter terminates nodes when they are underutilized to save cost and optimize resource usage. Core functionalities of the Karpenter. Karpenter automatically provides provisions new nodes when pod can't schedule. It's removed underutilized or unutilized nodes when they are not much needed. It supports variety of compute options to suit like different workloads. It makes real-time decision and optimize which nodes to use based on pod requirement, ensuring like efficient resource utilization and cost optimization. Then, so by leveraging Karpenter, organization can build more efficient, cost-effective, and responsive Kubernetes cluster, and that translates directly to the better application performance and smarter resource utilization. Let's look at some of the key benefits using Karpenter. Improved cluster efficiency. Like Karpenter dynamically provision just the right kind of nodes, reducing underutilized resources, packing workloads more efficiently. Then enhanced application availability, like with rapid and intelligent scheduling and application experience, fewer delay or bottlenecks during the scaling node churn events, like it ensure high availability of the application. Then cost optimization, like with rapid and intelligent scheduling, application experience fewer delays or bottlenecks during the scheduling and ensures and especially in dynamic environment, like it can significantly reduce infrastructure cost because work with the sport instances as well and use the efficient node, like which is exactly needed for the pods, right? And then flexibility to varying workloads, like it is highly adaptable, like it work for the all kind of applications and workloads, like for example, ML workloads nowadays, that it efficiently work with the ML's workloads as well. And then reduce operational overhead, like it is highly adaptable whether you are running busty jobs or long-running services, anything, right? And simplified operations, like all of this leads to simpler cluster operation, especially when paired with tools like provisioner, consolidation logic, and disruption budget. In short, Karpenter is not just about auto-scaling, it's about making our Kubernetes infrastructure smarter, leaner, and more developer-friendly. Then node churning and why it is actually a challenge. Node churning. So when like nodes within a Kubernetes cluster are frequently created and terminated with a shorter period or high rate of over a particular time. This is called node churning. This is continuous cycle of provisioning and deprovisioning nodes lead to cluster instability and can reduce overall cluster performance. Node churning is a problem because it disrupts the normal and stable operations of the clusters. And why node churning is a major issue? Few points which create it which demonstrate it a major node churning is a major issue, like reduced cluster stability. Frequent node changes cause unpredictable behavior in the cluster, making it difficult to maintain in a healthy environment. Then increased latency. New nodes take time to initialize fully, which can delay workload starting and affect application responsiveness. Then resource wastage, like constantly provisioning and terminated nodes consume more cloud resources than necessary, leading to the inefficiency. Then due to like wastage of a lot of resources, it like also leads to higher cost. Then degraded application performance, like workload might suffer disruption and interruptions when nodes are transitioning or replaced. Then increased operational overhead, like DevOps teams spend more time to troubleshoot those kind of issues. And potential data loss, like if node churning is not handled properly, it can cause data inconsistency and loss. So controlling node churn is critical for maintaining a stable environment, efficient and cost-effective Kubernetes environment. Now, at this point, I would like to hand it over to my colleague Shivani, who will guide you through the next few slides. You will be hearing her, like from her directly via video segment included in a few upcoming slides.
Thank you so much, Chetan. Hi again, everyone. I'm Shivani Mehrotra, a software development engineer at Expedia Group. I've been with the organization for almost past 2 years now. And in this segment, I'll walk you through the different Carpenter configurations that we have explored to address the major issue that we discussed earlier, which is node churning. We'll not only cover the configurations, but also deep dive into how the each test case was designed and the potential impact these settings can have on our running workloads. Before we look at the actual testing results, let me first highlight the key parameters that we evaluated across different scenarios. They were consolidate after, termination grace period, the expire after, and disruption budget. So these parameters played a crucial role in determining how efficiently Carpenter handled scaling and node churning in our environment. So let's start with the test case one, that is without termination grace period. In our first test case, we configured Carpenter's disruption settings to test how it handles the scaling when the nodes are underutilized or empty. We set the consolidation policy to when empty or underutilized, meaning that Carpenter should consolidate the nodes whenever they are not fully utilized. The consolidate after was set to 5 minutes, so the consolidation actions are only triggered if the nodes remains underutilized for that amount of duration. We left the termination grace period unset, meaning that Carpenter uses its default behavior when terminating nodes. The expire after parameter has been set to 600 seconds, which allows the nodes to be considered expired or eligible for replacement after 10 minutes. For the workload, we deployed a single replica of the application with a do not disrupt annotation, ensuring that Carpenter respects that pod and avoids evicting it during the consolidation. In terms of the disruption budget, as you will see on the left side, we allowed Carpenter to consolidate up to 10% of the nodes when they are underutilized or drifted, and 100% of the nodes when they are completely empty. This combination lets us observe how aggressively consolidation occurs without impacting critical workloads. So in this first test case, we have observed that we had a dedicated node pool running a single node specifically for this application pod. But after the expire after duration elapsed, the pod was not evicted because it was carrying the do not disrupt annotation. And as a result, the node remained running even after the configured expiration period. The summary of this test case was that the node did not get terminated after the expire after due to the presence of the do not disrupt annotation on the pod. This behavior ensures that the critical workloads marked with the do not disrupt annotation are protected from any kind of disruption, avoiding unintended downtime. However, because the expire after is not being enforced here, this can delay the node refresh operations, node replacement, recycle, etc., leaving the node running and until the do not disrupt pod either completes or it exits. Moving on to the test case 2, that is with termination grace period. In the first test case, we looked at the configuration and the consolidation behavior when we did not have any termination grace period set. But in this test case, we kept most of the disruption settings identical to the first scenario, but we introduced a termination grace period of 60 seconds. The consolidation policy remained set to when empty or underutilized, and consolidate after was set to 5 minutes, meaning that nodes are considered for consolidation only after being underutilized for that duration. The expire after parameter again was set to 600 seconds, marking the nodes as eligible for replacement after 10 minutes. We ran again a single replica of the application pod, still annotated with the do not disrupt annotation, ensuring that Karpenter respects its placement. The disruption budgets also remains unchanged in this test case, allowing up to again 10% of the nodes to be consolidated when underutilized or drifted, and 100% of the nodes when they are empty. By adding a termination grace period of 60 seconds, we aimed to observe how introducing a controlled shutdown period influences the node termination behavior in the presence of the do not disrupt pods, and whether it improves the node refresh cycle as compared to the previous test phase or not. So, what did we observe in this scenario? In this scenario, the application pod was running with the do not disrupt annotation earlier. Now, when this pod got deleted, the node is terminated only after the configured expire after period plus the termination grace period time interval is over. Once a node is terminated, a new node is automatically provisioned and the pod is rescheduled onto it. However, this introduces an additional delay. This additional delay is equal to the pod's startup time, that is, before it becomes fully operational again. So, the summary of this test case was a node does get terminated after the expire after plus termination grace period, even if there is a do not disrupt pod that is running in the current setup. This behavior ensures that nodes are eventually refreshed or expired, preventing indefinite node retention, regardless of all the PDB policies that we have in place. But in this case, a potential downside is that now, if the pod's own termination grace period seconds is longer than the node's termination grace period setting, then the pod may be forcefully terminated prematurely, leading to incomplete cleanup or disruption. But this approach can also introduce temporary downtime, as no replicas might be available or running during the combined termination and the pod reinitialization period. Moving on to the third test phase, that is the consolidation behavior when empty. In the third test phase, we wanted to observe Carpenter's consolidation behavior under conditions where nodes become either completely empty after serving a very high workload. We configured the consolidation policy to again when empty or underutilized and with the consolidate after set to 2 minutes, meaning the Carpenter checks for empty nodes or underutilized nodes more aggressively. We also set the termination grace period again to 60 seconds and the expire after to 600 seconds. Initially, we deployed the 50 replicas of the application, all carrying the do not disrupt annotation, and then we scaled down the replica count to 0, effectively leaving the nodes empty. The disruption budget again remained the same, allowing 10% of the nodes to be consolidated when underutilized or drifted, and 100% when empty. So, what did we observe in this third test phase? So, once the workload was scaled down to 0, earlier we had 50 replicas running, but when we scaled the replica count to 0, the nodes became completely empty. Carpenter, honoring the 100% budget for empty nodes, it terminated all the unused nodes after the consolidation after, plus the termination grace period interval. So, I think in this case, it was 2 minutes plus 1 minute of termination grace period. That's 3 minutes. This demonstrates that empty nodes are aggressively reclaimed, helping to optimize the costs and cluster utilization, even when the do not disrupt annotation is present. But in this case, even if the annotation was present, we did not have any replicas running. So if there were no pods that were remaining, uh, thus the nodes were reclaimed very aggressively because they were empty. This combined behavior ensures fast scale down and efficient cluster consolidation when workloads drain completely. Let's move on to our case 4, which is consolidation behavior with do not disrupt pods. So in case 4, we use the same configuration as the previous case to evaluate the consolidation behavior, but this time we made a minor change that we did not scale the application completely to zero. Instead, we started with 50 replicas of the application, each carrying the do not disrupt annotation, but later we scaled it down to only 5 replicas. The configuration remains unchanged. Like the consolidation policy was again when empty or underutilized. Consolidation after was set to 2 minutes. The termination grace period set to 60 seconds and expire after again set to 600 seconds. Now with 5 pods which were still running, each on the nodes annotated with the do not disrupt annotation, Carpenter did not consolidate or terminate these nodes even after the consolidation timer elapsed. This behavior is expected as the do not disrupt annotation prevents disruption of the critical workloads, ensuring that these remaining nodes which were running those 5 replicas were preserved until the pods exited naturally. Let's take a quick look at the observation for this test case scenario. The application had 50 replicas running initially. So when scaling an application from 50 replicas to 5, Carpenter initially provisioned a large instance type to handle the higher pod count. But after scaling down, consolidation was blocked by the do not disrupt annotation, thus preventing immediate downsizing to a smaller instance type. The disruption only occurred after the combined expire after, which was 10 minutes, plus termination grace period that was 1 minute time interval elapsed. At which point, Carpenter terminated the large node and then provisioned a smaller optimized instance type for the reduced workload. This demonstrates that do not disrupt annotated pods can delay Carpenter's consolidation behavior, thus preventing timely right sizing of the nodes until the expiration period is reached. Last but not the least, the final case, consolidation behavior without any do not disrupt pods. In this case, we repeated the same configuration as the previous one, but removed the do not disrupt annotation from the pods to observe how Carpenter consolidates the nodes without disruption restrictions. We started with 50 replicas, which led Carpenter to provision a large instance to handle the workload. When we scaled down to 5 replicas, Carpenter immediately evaluated consolidation. With no do not disrupt protection, consolidation occurred after the 2-minute consolidate after timer, followed by the 60-second termination grace period. The large instance was then terminated and a smaller node was provisioned to optimally handle the reduced workload. So, as we previously discussed, without the do not disrupt pods, the consolidation was not blocked. The larger instance was replaced with a smaller right-sized node after the consolidate after 2 minutes plus the termination grace period 1 minute time interval in total after 3 minutes. This behavior enables faster cost optimization and scaling efficiency compared to the cases where do not disrupt annotations are used. So these were few of the major test cases that we wanted to share with you all. But what is our recommendation after performing this testing? So the termination grace period defines how long Carpenter will wait before forcefully deleting a node. If the pods cannot be evicted due to the pod disruption budget constraints, example do not disrupt, max unavailable set to 0, then they will be forcefully terminated once this grace period expires. Additionally, the PDB rules can extend the workload migration time beyond the configured expire after, even when a replacement node is already available, since these rules still apply during the pod rescheduling. To minimize the disruption and improve consolidation efficiency, we recommend isolating the PDB constrained pods, example, the do not disrupt workloads, onto the dedicated node pools, allowing other nodes to scale down or be replaced without any delay. So, to discuss our recommendations in more detail, we have designed 3 different node pool strategies that can be used to intelligently distribute the workloads, minimize the disruptions, and mitigate issues like node churning. That's all my part. Handing over to Chetan to proceed to the next segment. Thank you.
Thanks to Shivani for walking us through our Karpenter configurations. Now I'll take you through the result and analysis section. We have explored 3 different node pool strategy. Let's start with the first one. So this is our first node pool strategy. We have like mentioned here different 2 node pools. Like one is the dedicated node pools for critical workloads. So this node pool is designed to host applications that are highly sensitive to disruption, like those who with do not disruption annotation, and that requires high availability. To avoid unnecessary termination, we have set expire after 220 days in this, so nodes are kept longer. Node defined a terminate grace period, allowing port to respect PDBs, and delayed consolidation using consolidate after 35 minutes to reduce frequent rescheduling. And then we have other node pool that is for the existing workload node pool. This pool handles everything else, all other non-critical applications. It also uses the expire after 20 days, but has a defined termination grace period of 1 day. Default disruption budget are applied here, and the same 35 minutes consolidation window applies. This helps us to strike a balance between stability and cost efficiency for less sensitive workloads. And then few action from the application team also needed, like for this strategy to work, application teams need to identify like which workloads are truly critical and should not be disrupted, and they need to add some node selector and then affinity and anti-affinity to their application placement is right. And then benefit to this node pool strategy, this have controlled node refresh cycle, ensured like this ensured predictable node life cycle and minimize the unnecessary termination. Then other is like protection for critical and do not disrupt workloads, like critical applications remain more stable. And then limitation blast radius during disruption. So isolate this also isolate like workloads across node pool, reduce impact of the node churning. And then optimize resource allocation, like as we use tailored node configuration, so that improves utilization and cost efficiency overall. This is our second node pool strategy, which introduced slightly more granular and split of workloads compared to the previous approach. Here we categorize application into do not disturb workload, critical workload, and then standard workloads. Dedicated node pool for do not disturb workloads. This is strictly for the application marked with do not disturb annotations. These apps are highly sensitive and like rescheduling or restart. We do not set a termination grace period here to like obviously to honor PDBs, and the nodes in this pool are longer, expire after 20 days, and conservative consolidation and like 35 minutes to avoid frequent node recycling. And then we have a dedicated node pool for critical workloads. These are like high available and business critical services that tolerate minimum disruption. Here we have configured like expire after 20 days, termination grace period of 4 days for safe shutdown, and consolidate after 35 minutes. We also define a custom disruption budget here. It includes specific schedule like running at daily at particular time, and then limit disruption to set a percentage of nodes at time. For example, we have mentioned 20% here, and then restrict consolidation based on the reason, like underutilized or drift helps maintain control over the like when or how nodes are consolidated. Then we have third, that is standard workload node pool. This node pool handles all remaining workloads, typically stateless or less sensitive apps. So uses like we use similar kind of application here, like expire after 20 days, terminus grace period 1 day, then consolidate after 35 minutes. It also uses the same disruption budget as critical pool, but with slightly more relaxed expectations. And then the similar kind of requirement from the application team, like to identify workload and then using like proper affinity and node affinity. Benefit of this node pool is like again controlled node refresh recycle, then fine grained control over the disruption, and then reduce blast radius. Obviously with this configuration, the blast radius is reduced to very less, and optimize resource allocations. Then we have our last third node pool strategy, a more simplified model compared to the second one. So it has two different node pools. Like one is dedicated node pool for the do not disturb workload. This pool is used exclusively for the workload marked with do not disturb annotation. These are sensitive applications that must not be interrupted during scaling, upgrade, and consolidation. In this setup, we have set like configuration like expire after 20 days, and we do not configure a terminus grace period here, and like allow or PDB disruption budget. And then this also ensure these workload are completely protected from node churn and voluntary disruption. The other node pool is standard workload node pool. This node pool handles all remaining workload, including both standard and critical application. This idea is to consolidate what's not explicitly marked as do not disturb into a shared and control environment. Then configuration we kept here like expire after 20 days and termination grace period as 4 days, and default disruption budget applied here. Like while not as an isolated strategy as like 2, but this still protects important workload within like longer eviction window, right? Then similar kind of requirement from the application as well. So benefits from this node pool is like this protect only do not disturb workloads from disruption and node churning. And then for standard workload, that a 4-day termination grace period ensure graceful exit before we force termination. So while these all three strategies offer a different level of control, but we encourage adopting the second node pool strategy as it strikes right balance between workload disruption, tolerance, and operation efficiency. Thanks. That was it for today, and thanks for tuning in. We hope we gave a clear like picture of how smartly like node provisioning, node churning we can use in the with the Karpenter, and that can boost our sustainability in the Kubernetes cluster. So if you would like to like connect or continue the conversation, our Instagram handle, LinkedIn handles are here, so we can connect over there. Thank you.